Alright, so the statement reads, a thin insulating rod running from z equals negative a to z equals positive a carries the indicated line charges. In each case, find the leading term in a multipole expansion of the potential, where a is lambda equal k cosine pi z over 2a, b equals lambda equal k sine pi z over a, and c equal lambda k cosine pi z over a, where k is a constant. Alright, so for our solution, let's consider the multipole expansion by its definition, where we have both the summation and the integral. Here for our situation, we note that r prime is just z, therefore Pn, the Lagrange polynomial, is just a function of cosine theta. The charge distribution is just a line charge, no volume needed, therefore d tau is just dz. Knowing this, we can substitute in everything, including the bounds, which run from negative a to a, and we could factor out the Lagrange polynomials and keep them outside the integral. And we can therefore call the integral with zn and the charge distribution lambda in for the sake of chugging through these problems with relative ease. The first term in this multipole expansion is known as the monopole term, or for the case when n equals 0. Plugging in n equals 0, we see that z to the 0 k cosine pi z to the 2a leads to an integral that actually is expressible and non-zero, and therefore we can plug that into the summation and get the leading term in this expansion. This is nice that we only have to evaluate one integral for this first case. The second and third cases will take a little more work. For case B, we have to still try to see if the monopole term exists. Here we know that it's not going to happen since sine is an odd function over symmetric bounds, which cancel to 0, which we see here. So going to what's now known as the dipole term, or n equals 1, we see that we have an integral that is now an odd and an odd, so we can evaluate it since z is odd over negative a to a and sine is odd over negative a to a. So as you see here, when evaluating an integral, it becomes kind of clunky, and we just have to be very careful. With all the arguments having to be u-subbed out and creating new coefficients, we have to be able to keep track of those and the plus or minus signs for the cases. But indeed, we see that we come to a nice compact fraction, and we can plug that into the formula that we had before. Note that we have to expand this to n equals 1, so we have a case for I0 and I1, but I0, if you recall, is 0, so it goes to 0. For the case that n equals 1 or I1, we have to also put in the Lagrange polynomial P1, which is just cosine theta. With that, we see that the leading term in this expansion is a dipole term, and it approximates as such. As you may have guessed, for our third case, we are not going to have anything easier, so we're probably going to have to do more work. Starting with this I0 case, which ends up canceling to 0, we have to now move on to the I1 case, or the dipole term. This, even though it's a much more lengthy integral, still cancels to 0 when you evaluate it and simplify with the algebra, which you see here. After that simplifies, we now need to move on to the n equal 2 case, or the quadrupole term. We see here that the integral is now again a much more messy integral to deal with, since we have z squared and a sine in there, and we'll have to break that up. Using an online calculator, you can quickly see what that needs to be evaluated to, and then once you do the algebra and plugging in and simplifying, you see that it takes a little more work, but we come down to a nice fraction as well, negative 4a cubed k over pi squared. So when we're trying to resub this back into the expansion, we need to run through the cases of I equals 0, I0, I1, and I2 in the multipole expansion. But note that I0 and I1 both go to 0, so we're only left with the I equal 2 case as our leading term. Since n equals 2, we need to plug that into both the denominator and the numerator of the summation, which would lead us to p sub 2 of cosine theta, the third Lagrange polynomial, and r cubed, since it's n plus 1, times the integral that we just found. Putting this all together, we see what the potential of the quadrupole term is, and that will bring this problem to its conclusion.